Welcome to tutorial 4, which will show you how to load image textures in OpenGL. It's based on tutorial 2, where we drew a rectangle and a triangle, but this time, instead of directly applying our own colour values to colour in the fragments, we're now going to load image files such as JPEGs or PNGs and apply those to the mesh faces. The animated texture effects that you can see on screen right now, apart from the bottom right spinning cube demonstration, which is simply a slight modification to tutorial 3, require only a few lines of code within the fragment shader to achieve the effect. Basically what happens is that in the case of a rectangle, for example, instead of simply applying the rectangular image such that the left edge of the image applies to the left side of the rectangle, the right edge to the right side, the top to the top and the bottom to the bottom, we can quite easily deform or distort those corresponding texture coordinates in a variety of different ways, such that they no longer correspond to the same positions or even map to the mesh face uniformly. However, before we get into the details of how all that works, we first need to understand how to load an image into computer memory to use within our app or game. So first we need to download an image loading library, and the one that's most commonly used for OpenGL is STB Image Loader. Once the page opens, scroll down the page and click on the stbimage.h link. Notice that the whole library is just one very large file, which we simply copy by clicking the Copy Raw Contents button and then pasting it into a new header file that we add to our project solution back in Visual Studio, and of course we need to include it at the top of the main.cpp file. To load an image, you first need to place it inside your solution's release folder. You then need to add the Load Texture Image function prototype and its function body, the details of which we'll look at in a moment, but for now we can just call the function and pass in our image name as the argument. GL Active Texture takes one argument, which is the enumerator that refers to the OpenGL texture unit that we want to make active. GL Bind Texture takes two arguments, the first being the target as a texture type, and the second being the handle that refers to your image. GL Uniform 1i, GL Get Uniform Location, set the shader sampler to the integer that corresponds to the texture unit that the image is bound to. The next several lines of code simply control the two scroll values which are passed to the fragment shader's scroll texture uniform. Loading an image into our application requires just a single call to the stbi load function. In addition to the file name argument, we also provide the address of the variables, width, height and number of components, which are passed to the GL texture image function to simply tell OpenGL about those particular image details. The next two lines of code are where it starts to get interesting, allowing us to set the behaviour of how OpenGL handles selecting which pixels to display if the texture coordinates happen to be outside the clamped range 0 to 1. As an example, let's take another look at the first two demos from the beginning of the video and compare the effects of GL Repeat versus GL Mirrored Repeat as the options for GL Texture Wrap. The Orange Beetles example is using GL Repeat, which as you can see simply repeats the image whenever the texture coordinates fall outside the range 0 to 1, which causes the image to be displayed back at the start of whichever axis of texture coordinates are being changed, which in this instance is the horizontal axis. GL Mirrored Repeat continues rendering the image in the same direction on screen, but reverses the mapping direction instead of going back to the start, which results in the eagles being displayed as mirror images of one another. GL Clamp to Edge sticks to using the very last pixel at the edge of the image, which as you can see results in an elongated stretch of that same pixel colour. And the last option is GL Clamp to Border, which fills in the non-existent pixel data referenced by any texture coordinates that fall outside the range 0 to 1, with a colour of our choice. Another cool trick is to make the fragment shader perform this clamp to border method ourselves, which we can do by checking the scrolling texture coordinate values within the fragment shader and then replacing the red, green and blue colour values accordingly, which has the advantage of giving us more control over the pixel colours, allowing us to produce a colour spectrum, for example. The next few lines of code allow us to play around with how OpenGL handles mapping the actual size of the image in pixels as per the JPEG or PNG file itself to the size of the image as it becomes displayed on screen. The GL Texture Min filter, which is the minifying filter, comes into play whenever the image size as displayed on screen is smaller than the actual size of the image, whereby GL Generate Mipmap, which was called earlier, has already created several gradually smaller copies of the image. The nearest pixel or an interpolation then becomes the colour that is used by OpenGL. This mipmap process makes the rendering process more efficient by avoiding having to read unnecessarily large images. As an example, I'm going to compile and run the program using the leaves image, first with the minifying filter set to GL nearest and then set to GL linear, and then I'll zoom in using Photoshop to exaggerate the visual difference between the two options. As you can see, the GL nearest setting produces the sharpest result, whereas GL linear makes everything look smoother, and so whichever one you prefer is ultimately just personal preference. Similarly, the GL texture mag filter, which is the magnification filter, comes into play whenever the image size as displayed on screen is larger than the actual size of the image, but in contrast to creating several gradually smaller copies, as used by the minifying filter, instead, the selected pixel is either the nearest pixel that the image size on screen maps to, or it's a linear interpolation of the pixels that it maps in between of. As an example, I'm now going to display a very low resolution set of different size and colour rectangles drawn as a single image that is only 25 pixels wide by 14 pixels high. As you can see, the visual difference between GL nearest and GL linear is extremely noticeable. However, unlike for the minifying filter, avoiding having to read unnecessarily large images obviously doesn't apply, simply because this time it's that the image is not actually large enough, and therefore it's effectively treated as magnified. We'll finish off this tutorial by looking at how animating and distorting images can be programmed within the fragment shader to produce some quite amusing graphics special effects, albeit they are rather basic. This first effect is achieved by simply adding the uniform scroll texture values to the actual texture coordinates set up on the CPU side via the vertex buffer object, which are then first received within the vertex shader. This adding of the scroll values then causes the image to be displayed as animated by travelling across the mesh face. The second effect is somewhat more amusing, in that the texture coordinates are either rotated only, based on the scroll value, or instead are rotated and stretched based on the scroll value multiplied by the varying APOS value. The transformation matrix is borrowed from the blade bending RCS teaser tutorial, which demonstrates how to transform or map vertices around a circle using basic trigonometry, which is the technique that I use for bending the helicopter blades. And the final effect being demonstrated for this tutorial is to choose between either making the beetle spots 100% transparent or instead setting them to a specific colour.